Welcome to the GeoMethod channel. Today we are solving another interesting geometry problem. Here is today's challenge. Can you find area of the green shaded triangle? Take a moment to study the figure. Then let us uncover the key geometric ideas that make the solution click. The green shape is triangle CDE, tucked into corner C, with D sitting on side BC and E sitting on side AC. Our whole job is to find its area, so let us gather what the figure gives us. The white region next to it, quadrilateral ABDE, is given to have area 50. This is our one number, so the plan is to turn it into a fact about our shared length. Matching tick marks tell us that segment DE equals segment BD. Let us give this shared length the single name A, so every length we meet can be written in terms of it. The angle at corner C between segment CD and segment CE measures 30 degrees. That is the sharp angle of the green triangle, and it will let us pin down its shape later. The two angles marked X belong to the large triangle ABC, angle BAC at A and angle ABC at B. They are equal givens from the original problem. We will calculate their value only after the setup is complete. So triangle BDE has two equal legs, segment BD and segment DE, each of length A meeting at a right angle. Recognizing it as a right isosceles triangle makes its area easy to write down next. For a right triangle, the area is 1/2 of one leg times the other. Here that is 1/2 times A, which is A squared over 2, and we will pair this with a twin triangle in a moment. Now draw the segment from B to E. This diagonal is the key auxiliary line because it slices the quadrilateral ABDE into two triangles we can compare. The diagonal BE cuts quadrilateral ABDE into triangle ABE and triangle BDE. So the quadrilateral's area is simply the sum of these two triangle areas. Now, use the source angles in the large triangle. Since x plus 30 degrees is 180 degrees, x is 75 degrees. Right isosceles triangle BDE gives angle DBE equal to 45 degrees. So angle ABE is 75 minus 45, or 30 degrees. Then triangle ABE has 75 degrees at A and E. Hence, segment AB equals segment BE, with segment BD equal to segment DE equal to A. Segment BE is a root 2. Therefore, the distance from A to segment BE is segment AB sine 30 degrees, or a root 2 over 2, while the distance from D to segment BE is segment BD sine 45 degrees, also a root 2 over 2. The two triangles on base segment BE have equal heights, so they have equal areas. Because those two triangles are equal in area, triangle ABE also measures A squared over 2. Both halves of the quadrilateral now carry the same clean expression. Adding the two equal pieces, A squared over 2 plus A squared over 2 gives exactly A squared. So the whole quadrilateral IBDE has area A squared. But that quadrilateral area was given as 50. Setting a squared equal to 50, we have found the one number that unlocks the green triangle. A second insight now finishes the structure. The green piece is a 30-60-90 triangle. The angles of any triangle add to 180 degrees. Subtracting the 30 and the 90 leaves 60 degrees at E. So see, DE is a 30-60-90 triangle. Leg segment DE sits directly across from the 30-degree angle at C, and we already named its length A. In a 30, 60, 90 triangle, this is the short leg, which we will use to reach the long leg. From vertex C, the tangent of 30 degrees is the opposite leg segment DE over the adjacent leg segment DC, and the tangent of 30 degrees is 1 over root 3, giving us an equation for segment DC. Rearranging, segment DC equals segment DE divided by 1 over root 3, which is a times root 3. The adjacent leg of the green triangle is a root 3. The green triangle is right-angled at D, so its area is 1/2 of leg segment DE times leg segment DC. That is 1/2 times A times a root 3. Grouping the A with the other A gives an A squared, so the area tidies to root 3 over 2 times A squared. Now it is written in the very quantity we already found. Replace A squared with 50, the value we recovered from the quadrilateral. The green area becomes root 3 over 2 times 50. 50 over 2 is 25, so the area is 25 root 3. That is the exact area of the green triangle. As a check, root 3 is about 1.732. So 25 root 3 is roughly 43.3 square units, a believable size for the corner. The green triangle CDE has area 25 root 3. That completes the solution. A good geometry problem often has more than one beautiful solution. If you see a genuinely different construction, a high-level idea that leads to another solution, or a thoughtful adaptation of an existing method, share it in the comments. Even a rough idea is welcome. A sketch of the key move is enough. We greatly appreciate these contributions. With your permission, we may feature the approach in a future Viewer Solutions episode and acknowledge you by name or channel handle. Thanks for exploring geometry with GeoMethod.